So first of all, just a quick reminder of our upcoming schedule. So today we're going to talk about actually the very first inferential spatial statistics well, not the first one, but actually the first group. They're about calculating patterns or measuring patterns of feature locations. And also we're going to work on lab 4 this Wednesday. And the next week, we're going to continue this conversation about measuring patterns. However, next week will be on feature values. And lab 5 is next week. And then after next week, we're going to have the exam work days. So basically, the two class meeting days, we're going to just use the class meeting time to work on the midterm. Like I said, it's totally open note. So I will also give you study guide maybe later this week so that you can start getting ready for the midterm. There will be a practical portion and also a quiz portion. And also just a quick question for the graduate students. I know we're missing a few graduate students here. So I have been in touch with our librarians. So I mentioned last week about basically having a session with our librarians so that you can get some training on getting research resources and also learning more about the database. So the problem is he's not available because I'm thinking maybe it's the best to have you folks meet on Wednesdays during the weekday, during the workday. Just, it would be easier for us to find the time together. However, he's not available this Wednesday. So how about we postpone our deadline for turning in the proposal to the following week, and so that you can meet with him maybe next Wednesday. So how about this? Does that sound doable? And also, so basically, what we can do is the graduate students, for those of you who are willing to meet with our librarian, you can skip the work day. And also, because for the lab, we can meet after class to help you figure things out. And in that case, will be, basically during the lab work day, if you're going to meet with the librarian, you are going to join his Zoom session, and so that you folks can talk about the research. So which will be, October the 7th. And also we're going to postpone our graduate project proposal to the 12th. So how about that?
That sounds fine, Ting, to me.
Okay, and also if you're willing to turn in the proposal early, you can still do, like just however early you want. But I felt like we can take more time and also get some training. Our librarian, actually, he has a background in geography. I took his workshop back in the summer. I felt like he must have more to share, not only about showing you how to navigate through the database. You probably can talk to him regarding how to put together a research and the general idea of a literature review. So if that works for you, I will be emailing the graduate students to confirm, and also I'll make sure to just let you know how that works. But as long as we have a few folks joining the research session, that'll be awesome. Okay. So let's get started on what we have for today. And also for today, we're going to have, so basically, as you folks write in the chapter, we're going to introduce 3 different methods for pattern analysis. And we will have a hands-on portion for you to do the calculation manually. So today is our, because so far, we have been just kind of like showing you folks the equation without really having to look into too much about the equation. But today you have to do the calculation manually. Okay. So for pattern analysis, first of all, just a big picture idea. Now we're starting to talk about inferential statistics, which means whenever we're introducing a method, we're going to talk about how the z-score and p-values are calculated and whether the pattern is significant or not. So basically it's different than the descriptive statistics we have been talking about so far. So in terms of pattern analysis, in terms of all the different techniques we're going to introduce, we classify the patterns in the basically 3 general categories. the patterns can be random or clustered or dispersed. So basically, like if you look at a pattern of a few point features, clustered means there are some smaller clustered across the study area, and dispersed is on the other end of the spectrum. So they are just perfectly dispersed, scattered around in your study area. And also just to follow up, I think last time we had this question about what's the difference between random and dispersed. So the difference between random and dispersed is random is right in the middle between dispersed and clustered. So which means if you have a random pattern, you will see some clustering, but also some dispersed. So here is the difference. Let's just make sure like visually we know the difference, because personally I do see whenever somehow I see a dispersed pattern, I feel like it's random. However, it's not random. Random must have also some degree of clustering. So it's half clustering and half dispersed. And also, for spatial statistics, for the inferential statistics, we also distinguish between global versus local statistics. So as you folks read or also did in the quiz, global statistics measure a single value, measure a single statistics for your entire study area. And also just, to match our schedule. So basically, before the midterm, we're only going to talk about global statistics, which means before the midterm, we're going to only calculate one single statistic for your entire study area so that we know overall is scattered or clustered or random. However, the global statistics doesn't show you the spatial variation. For example, the global statistics doesn't identify the local clusters. It doesn't also show you like clustering of high values or low values. And those are all falling into the category of local statistics. And we'll be talking about local statistics after the midterm. And local statistics basically will calculate one single value for every single feature in your study area. So this is the bigger distinction, but we focus on global before the midterm. And also, just similar to the descriptive statistics we have been talking about so far, like whenever we're introducing a method for calculating center or dispersion, we can calculate the method for the feature location itself, and also, we can calculate the pattern by using a weighted field, so by using weights. So very similar idea, for the pattern analysis, we can measure patterns for feature locations itself, for example, for the point locations itself. But in addition, we can also calculating the patterns of the attributes, patterns of the feature values, so that we can also say the values are dispersed or clustered, and we're going to talk about feature values next week. So today, we're going to focus on global pattern of feature locations. So which means you're going to calculate, whether, the points features are located, are dispersed or clustered, or, some polygons are dispersed or clustered. And you'll see some more examples in the lab as well. So just a quick review of the three methods that are covered in the chapter. So the first one, so basically the three different methods for measuring feature locations are the quadrant analysis, the nearest neighbor index, and also the K function. So today we're going to focus on how the three different methods work and what are the major difference. And also you are required to make sense of the calculation for quadrant analysis and nearest neighbor. So I will give you something for you to calculate manually. And also for the K function, we'll introduce how K function works and how do you interpret the results. And also, since we are basically talking about inferential statistics, so today we're also going to talk about whether the patterns are significant or not. So in order to make the decision of whether to reject the null hypothesis or not, we will have to, like for the three different methods, the key is to compare the observation, like what the data you have versus a hypothetical random pattern, random distribution, so that when your pattern is more clustered than the random distribution, then your pattern is clustered, and when your pattern is more dispersed than the hypothetical random, then it's going to be dispersed. So all the three different methods are really like working in a similar manner. However, of course, equations are different. Okay, so so let me show you a example of let me see what we can do with the worksheet. So for now, can you folks go? I can send you the worksheet, but also you can also go to D2L to download the worksheet. It's a Excel file. So let me try to get rid of my slides. I need to open up the worksheet. So I'll be sending you folks the worksheet, and you can open up the worksheet on your computer, and then I will basically explain how this works. So I'm going to send the worksheet through the chat. So you should be seeing a file called worksheet_September the 28th. So you can download the file from the chat area, or you can also download the worksheet from our D2L for today. So if you click on the worksheet from D2L, you should be seeing the same file. Let me see if I can open up the file on this computer, or maybe I should be joining with a different computer. So this worksheet actually has two different tabs. And each of the tabs is for a particular method we're going to talk about today. So let me join with a different computer, and so that I can show you how this works. And you can open up the worksheet and start looking at the instructions, and we'll definitely go over how every single step works. So I'm going to skip this slide first and just talk about how quadrant analysis works, so that we can be on the same page regarding how to use the worksheet to, basically work on the calculation. So for first of all, for the quadrant analysis, just a quick idea that ArcGIS actually doesn't implement quadrant analysis in as part of the toolbox. So which means for the new lab, we're only going to focus on the nearest neighbor and k-function. However, since quadrant analysis is a very commonly used method for many physical science, for example, for those of you who had some ecology classes before, you probably had this experience of out in the field and doing some quadrant analysis to measure species distribution. So the idea of quadrant analysis is you will be basically suppose you have a number of different point locations which can represent for example different crimes or different plant species. And the way a quadrant analysis works is by superimposing a set of quadrants, which basically is a grid of cells or equally sized areas. And usually we use squares, but also, like depending on, different programs you use, you can choose to use other R circles, and also, people may use hexagons, but by default, quadrant analysis would be using squares. So which also means, the scale matters, because if you use smaller squares versus large squares, your analysis results can be very different. So in order to make reasonable analysis, usually there's a recommended suggested size for the quadrant, so which is defined by this equation. So basically this equation means the area of individual quadrant, the area of the individual cell should be twice of the average area, depending on how many features you have. So it's basically twice of the average area per feature. And the reason why we take the square root is because usually we define the area by, because we said it's a square, so we usually define the area by one side of the length, the length of one side of the quadrant, and which is why we're taking the square root. And then also, once we have the quadrant superimposed on your study area, the second step is to count the numbers of features in each quadrant. So basically, we'll go over the steps together, but the idea is to count the number of features in each quadrant, and then we're going to create something called a frequency table. We're going to do the frequency table together, and also, just so you know, there will be one question in the midterm related to creating a frequency table. So for the quadrant analysis, really let's make sure you know how the frequency table works, and how to create a frequency table based on a set of quadrant and your study area. And then the last step is to compare your observed frequency, using your frequency table with a hypothetical random distribution. And this hypothetical random distribution is estimated based on the Poisson distribution, and it's using this particular equation. So the reason why the Poisson distribution is used is basically because Poisson distribution is used to estimate random event. So they're using the Poisson distribution to estimate the probability, like given a hypothetical random distribution in the same study area, the same number of features, how the distribution should look like. So the idea is really just to compare your observed pattern, like your current pattern, with a hypothetical random distribution. And in the worksheet, I actually have all these equations developed for you. So you don't have to really do this kind of calculation manually. So when you fill out the different numbers, the hypothetical random distribution will be popped up automatically. We can, later on, we can use the worksheet to go over things together so that we can better make sense. But now I just want to go over the processes. So basically, we're going to compare your observation with the hypothetical random distribution. So when your, basically when your quadrant, when your observation has more cells or has more quadrant containing many features than the random distribution, we would consider the pattern to be clustered, because they're just more concentrated in a few quadrants, and that's why if you have more quadrants containing more features, then the pattern is going to be clustered. And then basically vice versa. If you have your observation has less quadrants containing more features than the hypothetical, it's going to be more dispersed. So we're going to try this with our worksheet, and essentially the significance test. This part is optional, but also we can use the worksheet to go over how this works. Essentially, you're going to determine whether, of course, your pattern is going to be different than the hypothetical. So the significance test is going to help you determine whether the difference is significant or not. So let me switch to my second computer. And then I can share my worksheet here. Can you folks see my worksheet okay? Okay, so I hope we are all here on the same page. So basically, let's make sure to turn on the quadrat. That's the first tab we're working on. And then also now what I want you folks to do is to turn on your annotate, because I do need to collect some data on the fly. Yeah.
What do you mean? Our ability to annotate the right now?
Yes.
Okay.
Do you folks see the red, kind of the red square?
Yeah.
Yeah. Okay. So just let me explain what I'm doing here. So basically, if we were to do this in class, my idea was to measure the classroom seating patterns based on where you folks sit, and then we can decide whether you folks are sitting in a clustered pattern or dispersed pattern. But apparently now we're on Zoom, so it's not quite functional. So my idea is, everyone please draw a, just kind of using this square as our hypothetical classroom, and you can plot a point, just you can pin your location within this square just to show where you would like to sit if this is a virtual classroom. I hope that makes sense. Okay, you can draw anything. Okay, I think I will be, I'm here.
And how you do that?
Do you see, I think on top of your screen, you should be seeing, if you click on view options, you should find an option called annotate.
I don't see that.
Do you see like you are viewing Ting Liu's screen? If you hover on, like maybe hover on the screen where you're seeing the shared screen.
You have to take your cursor all the way to the top, and then some tabs might pop up.
Yeah, like you have to hover on, the top of your screen. So let me count. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. We're missing a few more locations. And if you don't see your annotate,
can you show me that on your screen, like where I should look for it?
So I'm not sure if my screen is the same as yours, but
because I don't have the upper part you got.
Yeah, you don't have, because I'm the host. So that's why our screens are different. So you can also let me know, maybe like at a particular corner, I can help you. So we don't have to, spend too much time on this annotate. So let me see the chat. Yeah, there should be something called view options. But if you don't have, you can let me know, and I can draw your points for you, Lena.
Well, I have there the view, like you have this home, insert, page layout. You mean that thing, like that view?
No, it's called view options. It's okay. If you don't see the option, if you click on view options, and there should be an option called annotate. But if you don't see it, we can just, I can just draw something for you so that we can quickly move on.
Well, draw whatever.
Okay. So I'm going to just draw another one. So
thank you.
Is everyone ready? Or maybe, I guess, for those of you who can annotate, feel free to draw a few more so that we have more data to work with. I feel like more data is probably better. Yeah, I guess I will just draw a few more. Okay. Okay. Okay, stop. We'll see how, like what the calculation will tell us about. All right, so now we have our pattern here. So basically, what we need for the pattern calculation for any of the methods you use, we need two primary information for the calculation to work. First of all, we need the area of your study area. So to, because we're on this virtual thing, so I would say to make things easier, I would say let's just do a 400 square feet, if you all agree with this, because it sounds like a regular size of the classroom, maybe slightly bigger than the one we usually have, but let's just do 400 because I feel like it's going to make the calculation a lot easier. So that would mean this square is 20 feet by 20 feet. So the area is 400 feet. So also you can enter 400 in your worksheet. Okay, so now it's tricky. Can someone help me count the number of features? I can count as well, but I just want to make sure. So what is this? 5, 6.
24, Ting?
I got 23.
Ah, see.
I got 23 without counting this one. Yeah, I think
23.
I have 23. Can we confirm it's 23? Yes?
Yeah.
Okay, cool.
Yeah.
So let's just do 23 and make sure you have these two things filled out. Number of features is 23 and extent of study area is 400 square feet. And so basically now you can see, well, this is getting a bit trickier. Can I just slightly manipulate the data because I want to make the calculation a little simpler. So let me remove a few more points. Two more, and then so I need to remove 3 more maybe. So yeah, I'm kind of lost. I was at 21, so I need to remove 3 more. Or maybe, yeah, I will do 3 more. And there's a reason. I will explain why I'm just changing the numbers. Eraser, and then I'm going to delete 3 more. Okay. So now we should be good to go. 1, 2, 3, 4, 5, 6, 7, 8. Okay, we should be good. So the reason why I want to change the number is because we need to determine, so the size of this quadrant is determined based on the number of features and extent of the study area. So I want to have a number that can roughly divide our study area into a 3 by 3 quadrant. So I know it's not perfect, but I felt like, it's kind of close. The 3 times of 6.5 should be very close to 20. So, let's jump in, feel free to jump in if you have any questions. So now I'm going to further, I just couldn't hover around. I think that's a problem of, this little thing. So let me draw. So 1/3 should be roughly here. Yeah, I'll just do this. I'm not entirely sure. It may not be perfect, but I felt like, as long as it's roughly the idea, we should be good. Okay, so now I'm just basically do a 3 by 3 quadrant based on what we have, for this study area. So also, let me take a screen capture so that I can share this with you folks after class.
I don't know if it'll matter for the calculations, but you've still got 19 for number of features. I think you dropped it down to 18.
Oh, did I drop it down to 18? Right, you're right. Can someone help me add one more point? And thanks for pointing that out. It does matter, Blake. Okay, cool, thanks. Like how many, yeah, I guess I should be. So how many, so, but we need something within the, definitely within the study area. I can draw one more. Okay, this one more, yes?
Yeah, I didn't realize when I tried to draw it, deleted my first one.
Okay. Okay, so now we're good. Cool. So now we're ready to go. So basically now we're ready to do the second step to build the frequency table. So let's really do this together because there will be an exam question and I do want you to know how to build the frequency table. So what this means is, for the frequency table, we're basically to count, for example, for 0, that means how many of the quadrant contains 0 features. And for the 1 feature, basically we're going to count how many of the quadrant are containing 1 feature, and just, and so on and so forth. How many of the quadrants are containing 2 features? That makes sense. So can we just do the numbers together? For 0, for the first row, for 0 features, how many quads we have containing 0?
0.
So that'll be 0. And what about for 1? I know some of them are in between, so let's count this green one to the to the quadrant below. So that was my I should have drawn the line a little better.
So there's 4.
4, yeah.
Okay, so there are 4, right? Let me just try to clear this. I'll just make sure things are little. Just make sure things are little.
Professor Singh, I have a question.
Yes.
Are we counting the quadrants by 1, 2, 3, then 4, 5, 6, and now 1, 2, 3 going to the bottom, right? So just 1, 2, 3.
No, so
right
we're not indexing the quadrats. We're basically counting the number of quadrats containing the number of features. So the reason why we have
4, and
right,
the other one will be 4, and then maybe 1.
Yeah, so this one will be 4 because we have 1, 2, 3, 4, right? And for the for 2, how many? 2 features.
2.
2.
3.
We have 1 and 2, so there are 2.
So right in the middle, the bottom, isn't it? Oh, there's 3 features. My bad.
There's 3. There's 3.
Yeah.
Let's do 3. I know it's just because we are like using the random symbols. Yeah. So how many has 3?
1.
1. How many has 4?
2.
2. And now we're done because as you can see, the total number of quadrats reaches 9, so which means we're ready to go. Okay. And now, as you can see, basically for the worksheet, we have filled out everything we need to fill out. So now, the observed number of quadrats, we have the number popped up, and also for the expected number of quadrats, we also have the expected number popped up based on the Poisson distribution, the equation mentioned in the book. So it's an idea of probability. So they're estimating, the corresponding expected quadrats based on a hypothetical random distribution. So now what we need to do is to compare the observed versus the expected. So basically the idea is if you have more quadrats containing more features than the expected one, then you can say, your pattern is going to be clustered. But if you have more quadrants containing fewer features, and then your pattern is going to be considered as dispersed. But here I can see that, our case is a little bit, it's trickier because, I can see it's kind of like we have more containing one single points, but also we have a little more containing four features. So that would probably indicate our patterns are random, or it's kind of in the middle. So it's a little bit hard to judge based on what we have. But I just want to quickly go over the idea. But I would like to mention that for the midterm exam, I only need you to know how to build a frequency table, so that you know how to summarize a frequency table using the quadrant analysis. So now, if you keep scroll down, the lambda, this just to estimate the frequency distribution is based on the number of features. So that's really how the expected number of quads are estimated. And eventually for this comparison, because eventually we're going to figure out whether your observed pattern, like what we have here, is really different than a hypothetical pattern. So to make the comparison, we're going to take the highest difference, the maximum difference between these two distributions, and which gives us the number of 0.12, because I've already built in the calculation here. So basically now we know the maximum difference is 0.112. And the next step is actually to find out a critical value based on this particular, I'll just call this test as the KS test. So that will give you a critical value, and then you can compare your maximum difference versus the critical value, and so that you can make the decision of whether the difference between your pattern versus the hypothetical pattern is significant or not. I should have the pattern table opened up. So if you click on, yeah, it's hard to see, but if you hover on your cursor to find the critical value using the KS table, you should be able to open up a PDF document like this. So this table is for you to look up for a critical value so that you can compare the two different patterns. Sorry, just like jumping around between the two different programs. And also, if you look at the table, as you can see, depending on your level of significance and the number of trials, so the number of trials in our case basically is the number of quads we have. So we have 3 by 3, so it's a 9. So if we take the 0.05, this particular 0.05 significance level, we can see the value, this critical value is 0.43. And we can see actually our maximum difference is less than the critical value. So we, the conclusion based on this is really like the pattern is random. So it kind of confirms our comparison, because we have sort of more patterns with fewer features. We also have more quads containing more features. More features, and the pattern is sort of random. And also, if you look at the pattern we have here, sort of like we have some clusters, but also we have some dispersed patterns. So based on this quadrant analysis, our final results is it's random. It's not really significant because our maximum difference between the expected pattern and our actual pattern is not that different. And also, once again, for step 4, it's optional because, I know many of you probably didn't have much background on the Poisson distribution on traditional statistics. But for the quadrant analysis, let's just make sure that you know how to build a frequency table. And that's the major thing required for the quadrant analysis. And quadrant analysis is not an option in ArcGIS. So in the lab, we won't focus on the quadrant analysis. Right. Are we ready to switch to the second tab? Or any more questions here?
Did you say that quadrant analysis is not available in ArcGIS? Or?
Right, it's not available in ArcGIS. So basically, whenever you have point locations, and if you're trying to analyze the patterns, by default in ArcGIS, it would be the nearest neighbor that we'll be talking about shortly.
Is that true for like open source GIS programs too?
I think Geoda might have quadrant analysis. That's what I remembered. So that's something we can take a look together after the midterm. So for the midterm exam, quadrant analysis is not the primary focus. So it's only required that you know how to build a frequency table. And we'll look at the quadrant analysis in Geoda after the midterm, because we have one day without a lab homework, I believe, and so that we can work on that part together. Amy, do you want to say something?
Oh no, sorry.
Okay. Okay. So feel free to jump in if you have more comments. But let's now move on to the nearest neighbor. And okay, so I think I still have to switch back to my another computer because I want to go over a few things together. Okay, for the nearest neighbor analysis, so this is also a very classic method that was first developed in 1950s. So basically, as you folks know, like when many of these methods developed, basically the calculation has to be manual because basically there's really no computer or GIS for you to do a spatial analysis. So the nearest neighbor index actually it does take into consideration of the distance explicitly. So basically how the nearest neighbor index works is by first of all, we can still imagine the patterns we have. So basically every single person or every single feature in your study area or in the virtual classroom has to first find out the nearest neighbor. And then you're going to calculate the distance from each of you to your nearest neighbor. And after that, we're going to measure or calculate the average nearest neighbor distance for all features. Basically that is to say, if you have several neighbors, you're going to measure the distance to your nearest neighbor. And then after that, we're going to take the average of the nearest neighbor distance of all of you. And after that, we'll also calculate, because the idea is to compare the actual pattern versus a expected hypothetical random distribution. And after that, we'll be calculating the expected average distance for a random distribution. And for this hypothetical random distribution, we would assume the expected average distance is actually halfway of the average area per, the average area. Basically, we're taking the square root of the average area per feature. That is to say, the expected random is right in the middle between a perfectly clustered pattern and a perfectly dispersed pattern. So when you have a perfectly clustered pattern, we know the average nearest neighbor distance should be 0, because in that case, it's a perfect cluster. So every single location will be on the same location. Every single feature will be on the same location. If you have a perfectly dispersed pattern, then basically every single feature should take the like its own single space. So that will be the average area per feature. So in order to decide on like the average distance for a random distribution, we're taking the half in the middle. That's the definition, because random distribution is in the middle of a clustered pattern and a dispersed pattern. So this equation basically measures the expected average distance for a random distribution. And after that, we'll be doing the comparison. So in order to do the comparison, there are two options, like the book mentioned. You can take the difference, and also you can take the ratio. That's really how we measure difference. We can measure basically the difference by doing a minus or by doing a division. But here we focus on the ratio by doing the division, because that's how ArcGIS calculates. So in ArcGIS, the nearest neighbor index is basically calculating the nearest neighbor ratio. So this is the equation is by dividing the observed average distance by the expected average distance. So now I have a question for you, just based on just based on logical thinking. For if your ratio is smaller than 1, do you think the pattern is clustered or dispersed? If the ratio is smaller than 1, it's less than 1. So basically,
it'd be clustered, I think, because the distance is shorter than expected.
Yeah, the distance is shorter. Basically, the features are closer than expected, so that's why it's clustered. And then, basically, if the ratio is greater than 1, then means the features are more distant than expected, so which means the pattern is going to be dispersed. But if the ratio is 1, that means your pattern is random. So that's the rough idea of how do you interpret the nearest neighbor ratio. Is basically you just compare the observed versus the expected average distance. And also, after you have the ratio, you kind of know, okay, my pattern is like clustered because the ratio is 0.8. However, you don't necessarily know if the 0.8 is significant or not. Maybe it's just kind of still in the random range, but you don't know whether it's significantly clustered or not. So in order to determine whether the difference or whether the ratio is significantly clustered or dispersed, we need to calculate the z-score. So the z-score is calculated by basically taking the difference between your observed average distance and your expected average distance, and it's divided by the standard error. So the standard error is basically the standard deviation of all the average distance around the average values. So by taking the division, we're basically normalizing the difference so that it represents the number of standard deviation on a standard normal distribution. And also, because we're seeing this kind of equation for the first time, I felt like many of you might feel confused. So two ideas. First of all, if you have taken traditional statistics, think about the student's t-test. So this structure is basically the t-test. But if you haven't taken any statistics, just keep in mind this basic structure when we calculate this score. So whenever we're doing the comparison, we're taking the difference between the observed and expected and divided by the standard error, we're calculating the z-score. So essentially all of this spatial statistics we're going to deal with from now on, whenever they're calculating their z-score, you should be seeing a similar structure of how the equation is being built. And also, if you're wondering how the standard error is calculated, is actually calculated based on this particular equation. So the idea is they're taking into consideration of the number of features in the study area and also the total size of the study area. And this point 26,136 is a constant. The general idea is they're just trying to measure the standard distribution of for a particular pattern, what would be the standard deviation from the average standard from the expected random distribution. And then once we have the z-score, we know the p-value can be derived from the z-score based on essentially if the p-value is calculating the total area, like as a curve that we mentioned, is kind of the two-tailed hypothesis. So there are some matching values. And again, this is something you don't really have to do the calculation because we know for this score, there are some critical values. And for the critical values, there are this corresponding p-values. And for the p-values, we know once it's very small, we can reject the null hypothesis that the pattern is random. So yeah, I feel like I know we have a second type in the worksheet, but I would like to go over, go through the K functions first before we, come back and work on the worksheet, just in case, because we do need to talk about the K function so that you folks can work on the lab. So any questions regarding the nearest neighbor index? So for the nearest neighbor index, we know we're calculating the ratio, which is the division. You're dividing your observed nearest neighbor distance by the hypothetical, by the random, so that once it's less than 1 once it's less than 1, then the pattern is clustered. But if it's greater than 1, the pattern is going to be dispersed. And now I'm also sending you folks a PDF document called the Nearest Neighbor Analysis Cheat Sheet. And this is something for you to keep. And next week, I'm going to give you another cheat sheet. So it's just some quick reference for you to interpret the patterns because, for each of the major analysis methods we're going to cover, each of them are have a set of ideas of how do you interpret the ratio and how do you analyze the z-score and the p-value. So this is one page for your reference and no need to memorize. You can use this for you to work on the labs and also work on the exam. So if you don't have any further questions, we're going to just talk about the K function first. And then we can see if we have time for the worksheet. Okay, for the K function. So the K function also takes into consideration of distance. However, it's actually a very interesting method that it gives you the idea of how your pattern change by distance, or basically how your pattern change across different scales. So, essentially the K function works by, the K stands for the number of the distance band you have. So you can define many different distance band, or you can only define a few distance band. So the K here stands for the number of the distance band. So it's sort of like, the buffers surrounding a particular feature. So the idea of the K function is, for example, now we have maybe a 1 mile distance band. So we're going to put this 1 mile distance band surrounding each feature in your study area. And then we're going to count the total number of neighbors falling inside your 1 mile distance band. And then we're going to take the sum of the, overall, like, how many, for example, how many neighbors are within a 1 mile, 2 mile, 3 mile distance band. So we're basically doing this count, summarizing the number of neighboring features falling inside the distance band across many different distance bands. So in that case, basically we're counting the numbers. So if we have more, essentially we're still comparing the pattern versus a hypothetical random distribution. So if we have more neighbors than the random, so basically if your number is greater than that for a random distribution, you can consider your pattern to be clustered. And that is because, there are more features, basically it's clustered. But if you have fewer points within a certain distance band compared to the random distribution, we're considering the patterns to be dispersed. So that is to say, within a particular distance band, there are not that many features. So we can sort of like consider this to be dispersed. So I'll just quickly show you how, what ArcGIS will generate, because that's really how what we'll be working with when you interpret the results. So let's make sure to spend enough time here and just make sense of the result. So when you run the K function in ArcGIS, just very similar to what we have been doing, you can just fill in your data, you can define a few options, and then you can generate, eventually part of your results will be this graphical report. So what does this mean? I mean, I'm sure you folks write about the general patterns within the book chapter, which looks really nice. But actually, if you're calculating the patterns for some real data, your patterns most likely are not very nice. So this is actually one of the best example I can give you. So let's spend some time here. So basically, this blue line represents the expected random distribution. So in ArcGIS, it actually takes the transformed K function. So the idea is once you did the transformation, the expected pattern will be plotted as the triangular line, this 45-degree line. And so that your data are not going up too high, you can just contain your data so that the expected pattern is going to be a 45-degree diagonal line. And also, of course, the x-axis represents the distance band, and the y-axis represents the transformed K function, the statistics. And the red line represents the observed pattern. So basically, the reason why we're seeing this plot is because we have multiple distance band. So I'm not sure if you folks can trace, the individual vertices on this curve. It's not really a curve because I only used 10. I think I only used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I only used 10 different distance band. So that is to say, basically at each distance, I will have a particular calculated K function value, and that will plot a curve like this. And also, like we mentioned, if you have more, basically we're counting the number. So if you have more points compared to the expected, so basically, if you're, for this portion where your red curve is above your expected blue curve, this portion is considered to be clustered. And for, wherever you have your observed pattern below the expected line, which means there are fewer points, that would say your pattern is dispersed because there are fewer points. So just a quick, just to check in and make sure we're on the same page. Well, I guess it's kind of, okay. So where do you see the pattern changed? Like at which distance do you see the pattern changed from clustered to dispersed?
800.
Yeah, roughly 800, and maybe we can go more precise, maybe like somewhere between maybe 850, but yeah, 800 seems to be the distance where the pattern changed. So basically where it crossed the expected line, it shows a pattern change from clustered to dispersed. And also, really ArcGIS is making our life a lot easier, because you don't even need to remember, which side, because you can see this side is clustered and the lower side is dispersed. So, they do give you enough information for you to interpret the results. Okay, so, and for those of you who are really interested in, how the transformed K function is calculated, you can refer to the page 99 for the equation. But essentially for the K function, I feel like observing the chart and also understanding the general idea of, basically they're counting numbers within the different distance band should be sufficient for you to understand how the K function works.
Ping, what are the units on the y-axis?
It's not labeled, but based on the data I have, it is feet. So it's similar to the idea we have been talking about. It's based on your layers projection. So it depends on the data you have. So in my particular case, it's feet that I know.
So on both axes, it's feet?
Oh no, it's only the x. So it's the distance.
Oh, but for the y-axis?
For the y, it's just there's no unit. It's just a K function, the statistics, the LD function based on the equation. So I would say there's no, because it's the number, essentially it represents the number of features. So there's no unit.
Ah, okay. Thank you.
And for the significance test of K functions, actually gets more interesting, because for the significance test, it's totally visual. So you'll be basically seeing the visual representation of the patterns. So let me explain using using the ArcGIS example. So essentially, we mentioned the red line, the red curve represents your observed pattern. And the blue line represents your expected pattern. And we know, for the portion above the blue line is clustered, and for the portion below the blue line is dispersed. And also, in addition to these two different information, so essentially, we can also have the option to kind of estimate this pattern multiple times, in which the program will generate an envelope. So the envelope, ideally, the envelope should really, perfectly surrounds your expected pattern. So the envelope represents the range of the random. So basically we know, okay, the blue line is random, but also, there's a range of the random. So it's not really too clustered or too dispersed, and they're still within this random range. So this envelope represents the higher and the lower confidence level, so that only the portion outside the envelope would represent, the significance portion. So which is to see, as you folks can see, only the highlighted portion, like for the above patterns, for the clustered patterns, only the portion that is above the upper confidence limit is considered as statistically significant clustering. And only the portion, like for the below portion, for the dispersed patterns, only the portion that is below the lower confidence limit is considered as significantly dispersed. So the idea is we're using the envelope. The envelope is calculated as a buffer. So only for the portion beyond or outside the envelopes are considered as significant. So this is really the ideal pattern. And also, when you actually start calculating the different patterns, you will likely see sometimes or very often that envelopes are not going to be generated very nicely. So sometimes you see weird patterns. And for that kind of things, we can, look at together on Wednesday. Just keep in mind that your patterns are not always going to be this nice. Sometimes there may be a mixture of, the envelope somehow just all falling below your expected pattern. That can happen, but this is an ideal case, and this is a general pattern. So just a quick comparison. For the three methods we have introduced today, the nearest neighbor index and K-function, they both consider distance. Essentially the distance is the key for determining whether the pattern is clustered or not for nearest neighbor, and also for K-function, you're basically doing a multiple scale analysis by looking at the pattern across a range of different distance band. And also for quadrant analysis, the size of the quadrant would matter. If you try different size of the quadrant, even though we do have suggested the best size, but if you try a smaller, if you try a bigger, that will give you different results. And also for the nearest neighbor and for the K-function, they both, they could both be affected by the shape of your study area. For example, if you have a smaller cluster near the border, near the edge of your study area, those portions will likely have some issues because you don't really know what is beyond the boundary. So that's really something that is common for our spatial data. For example, we look at things happening within the city of Chicago, but also like for the patterns around the border of Chicago, it may not be precise or accurate because the boundary is arbitrary, and things happened outside the boundary could likely have some interactions with things happening within the boundary. So edge effect is going to also affect our outcome as well. Just a quick reminder on the assignments. We have a lab 4 work day on Wednesday, so we're going to focus on nearest neighbor and K-function because the ArcGIS doesn't cover quadrant analysis. And we also will have a new reading quiz due before Monday's class. Let me see how many. Okay, we have 7 minutes left. I'll see if we can actually get started on the worksheet, the second tab of the worksheet, if you still have your documents. It's getting really dark. Let me see. I'll share my screen here. Okay, so now I'm back to my second tab of my worksheet. So we'll get started, and if we couldn't finish, I will post the final version to, yeah, I'm glad I took a screen capture of the pattern. So let's just first decide on, the information we need, and so that we are ready to take the calculation. So again, this is our pattern. So based on the idea that we know, for the nearest neighbor index, it's basically calculating the shortest distance between each feature and its neighbors, and then calculating the average shortest distance. And given that each side of our virtual classroom is like 20 feet, what would you say the average? So basically, we need to fill out, this particular cell, so that maybe we can take some time after class to do the calculation. So what would you say the observed average nearest neighbor distance should be? Does that make sense? So basically, we're just kind of estimating, for example, for this particular feature here. Let me see if I can do a spotlight. Okay. For example, for this feature, the shortest neighbor should be this one. So the distance would be the straight line distance between these two features. So essentially, for each feature, it's going to find its nearest neighbor and then measure the distance. And for the value we need to fill out for the observed average distance is the average of all pairs of shortest distance. I know like the estimation wouldn't be perfect, but I guess we can just sort of determine a value so that we can all move on with the same number.
Maybe like 3 feet, 3.5.
3.5. Yeah, that kind of, I think that makes sense. Yeah. Any different ideas? Blake said 3.5. Anyone wants a different number? So the, yeah.
5 feet?
5?
Yeah.
Mm-hmm. Yeah, because for some features there may be, yeah, but also, yeah, as I do see, for some features there are some short, like very short, like closely, like nearby features, and the distance would be short.
Just split it and go with 4 feet.
Can we do 4? Just kind of like in the middle. Okay. Yeah. So I would just do 4 here. Although, it's not perfect, but in ARC, the distance will be determined for you. So for 1.1, you can say it's 4. Again, it's based on just an estimation that we have determined based on our the virtual pattern. So for basically, let me explain how this works, and we can, if you get a chance to do the calculation later, Wednesday we can check in with the answers together. So you basically, for this second worksheet, you are going to do the calculation manually. So for this second worksheet, I do not have the equations built for you. So you will have to do the calculation yourself. You can use either Excel, or I guess to me, it's probably easier to use a calculator, Google Calculator, or a calculator on your computer. So the expected average distance is calculated by using this equation. So we know the number of features is 19 and the area is 400. It's still the same study area, so you still have the numbers. We can actually do this calculation together. Let me see if I can just use a Google calculator. So, well, actually, I'm going to use R maybe. Well, I don't have R here. Okay, so I'm going to do the calculation of 0.5 divided by, yeah, maybe I should be doing, I will just calculate the square root of 19 divided by 400 because n is the number of features, which is 19, and the area is the extent of the study area, which is 400. So if you're going to take the square root, is 0.22 roughly. I can just copy and paste. I'll copy the number and then I'll just do 0.5 divided by this number. So it gives me an expected average distance of 2.29. And basically you can calculate the ratio, the nearest neighbor ratio, by doing a division. I'll just do the division, and then we'll just wrap up for today because it's already 25. So we know essentially I'm going to just copy 2.29. So our observed is 4. So 4 divided by 2.29. That would give me 1 point, I'll just do 1. It's greater than 1 either way. So it looks like our pattern is going to be more dispersed because it's, the distance is greater than the expected. So now it's really, for the patterns, dispersed. Okay, so we'll just leave the second step and the third step. So essentially you're going to just plug in the equation and do the calculation to calculate a z-score. And you can go to the website to check the corresponding p-value for that z-score, and which will help you determine whether the pattern is significant or not. So I'll be doing the calculation, and like at the beginning of Wednesday, so we're going to just quickly check in and make sure we have the right number. I'll do my calculation, but also I want to have at least some of your numbers so that we know the numbers are correct. Essentially just plug in the equation and calculating the z-score and finding the p-value for the corresponding z-score. Okay, so that's all for today.